Imagine tracking a fault current through a massive transmission grid. You have a 132 kilovolt transmission line feeding through a transformer into a 33 kilovolt sub-transmission network, which steps down again into an 11 kilovolt distribution zone. Every time you cross a transformer, the voltage, current, and impedance values all change physically, requiring a new set of calculations just to keep your numbers balanced. The per-unit system fixes this. It expresses every quantity as a decimal fraction of a chosen base value. Instead of tracking a 138 kilovolt reading on a 132 kilovolt line, you just read 1.04 per unit. This reference text shows the core equations. To calculate a per-unit value, you take the actual quantity and divide it by a designated base quantity. To build this system, you only need to choose two independent starting parameters, your system base power, or S base, and your base voltage, or V base. Choosing these two bases provides a common reference point. Instead of juggling actual kilovolts on one side of a transformer and tens of kilovolts on the other, you shift the entire study onto a shared decimal scale. Let's map this onto a standard 3-bus system, featuring a generator, a transformer, and a transmission line. Notice how the transformer cuts the system into two distinct voltage zones. Every calculation in this network relies on a fixed power anchor. We typically choose 100 MVA as our system S base, and that value remains unchanged even as you pass through transformer boundaries into new zones. Base voltage behaves differently. It is tied to the physical turns ratio of the equipment. When you cross from the generator zone into the transmission zone, your base voltage must be stepped up or down by the exact ratio of that transformer. You track this zone-by-zone base voltage to calculate the base impedance for the transmission line. Using the industry-standard three-phase formula, base impedance equals your local zone's line-to-line kilovolts squared, divided by the universal three-phase base MVA. Equation 3.91 in this text shows the change of base formula. You will need this because manufacturers stamp per-unit impedance on equipment nameplates based on the unit's physical rating, say 50 MVA, not your 100 MVA system base. If you take a raw manufacturer impedance and plug it directly into a grid-wide study, your fault current calculations will fail. You have to convert the equipment's old base parameters to match your new system base parameters. Let's test this. You have a transformer nameplate showing 10% impedance on a 25 MVA base. Pause the video and convert this to a 100 MVA system base. To solve it, take the old per-unit value of 0.10 and multiply it by the new base power divided by the old base power. 100 divided by 25 is 4. The correct impedance for your model is 0.40 per unit. Catching that nameplate discrepancy and applying the change of base formula ensures a robust model. It is a mandatory step before any load flow analysis can begin. This diagram shows the final single-phase equivalent circuit in per unit. Because we normalized the voltages and powers, the ideal transformer physically disappears from the math. We are left with a simple voltage source and a string of series impedances. With the entire grid on a common base, you apply standard circuit algebra, a basic Ohm's law calculation. Voltage divided by total series impedance will now yield the exact fault current for the system. When you ingest a grid model, follow these three rules. Base power is universal, base voltage changes at every transformer, and never trust nameplate per unit data. Always change the base. Mastering this normalization process gives you the mathematical foundation to run infinite bus fault studies and iterative load flow algorithms. We will start building those in the next episode.